Lithium is the metal driving the modern energy revolution, powering electric vehicles, smartphones, laptops, drones, grid-scale batteries, and the global shift toward renewable energy. But behind every battery cell is an enormous industrial chain that begins deep underground or beneath ancient salt flats. Lithium does not come ready-made for batteries. It must be mined, concentrated, chemically processed, purified, crystallized, converted into battery-grade compounds, and shipped to cathode and anode factories with purity levels measured in fractions of a percent. And today on the How Factory, we're going inside that process to reveal how lithium is extracted, refined, transformed, and prepared for use in high-performance energy storage systems. What begins as rock or brine becomes one of the most critical materials in the modern world, but only after undergoing one of the most complex chemical manufacturing sequences in industry. The journey starts in two very different environments: hard rock lithium mines and brine-rich salt flats. In countries like Australia, lithium is found in spodumene ore, dense granite-like rock containing lithium locked inside mineral crystals. In South America's Atacama Desert, lithium-rich brine sits under vast salt flats, pumped to the surface from underground reservoirs. Though the processes differ, the end goal is the same: isolate lithium from everything else. Hard rock mines blast and crush spodumene ore using excavators, haul trucks, and jaw crushers. The crushed rock passes through screens and grinding mills that reduce it to fine particles. Flotation tanks mix the slurry with air bubbles and reagents, causing spodumene to float while impurities sink. The result is a concentrated spodumene product, usually around 6% lithium oxide, ready for chemical conversion. Brine extraction begins with drilling wells into lithium-rich aquifers. Brine, muddled in extremely salty water, is pumped into vast evaporation ponds that stretch for miles. Sunlight and dry desert air evaporate water gradually over months, increasing the concentration of lithium as minerals like sodium, potassium, and magnesium precipitate out. Workers and automated systems monitor the chemistry of each pond, transferring brine sequentially as it becomes richer in lithium. In the final ponds, lithium chloride reaches concentrations high enough for chemical extraction. While slower than hard rock mining, brine production is energy efficient due to the free evaporation cycle. However, both methods require careful environmental management to protect water systems and local ecosystems. Once concentrated, the next stage is chemical conversion, turning spodumene or brine into lithium compounds usable in batteries. For hard rock sources, concentrated spodumene is heated in rotary kilns to around 1,000 degrees Celsius. This roasting process transforms the mineral from alpha spodumene into beta spodumene, a more chemically reactive form. The roasted material is cooled and mixed with sulfuric acid in large digestion tanks. When heated, the acid leaches lithium from the mineral, forming lithium sulfate solution. This solution undergoes impurity removal in precipitation tanks where magnesium, iron, calcium, and aluminum are filtered out using chemical additives. Each impurity must be removed to extremely low levels because battery-grade lithium requires purity above 99.5%. For brine operations, lithium-rich brine enters chemical plants where it is treated with soda ash to precipitate lithium carbonate, a white powder commonly used in battery cathode manufacture. Magnesium and calcium removal steps ensure the resulting carbonate meets industrial standards. Some brine producers then convert lithium carbonate into lithium hydroxide, a compound increasingly used in high-nickel EV battery chemistries. Hydroxide production involves reacting carbonate with lime slurry, producing lithium hydroxide solution that is filtered, purified, and crystallized. Crystallization is one of the most sensitive steps. Lithium carbonate or lithium hydroxide solutions enter large evaporation or cooling crystallizers, towering stainless steel vessels that control temperature, agitation, concentration, and nucleation conditions. These conditions determine the crystal size, shape, and purity of the final product. Crystals are separated using centrifuges, washed with purified water, and dried in industrial dryers. Once dry, the powder is milled and sieved to achieve uniform particle size. Battery manufacturers demand extremely consistent granulometry because particle size affects how cathode powders mix and how battery electrodes perform. But before lithium compounds can be shipped to battery manufacturers, they must undergo rigorous purification. Ion exchange columns remove trace metals. Solvent extraction units further eliminate sodium and potassium. Filtration systems remove microscopic solids. Carbon polishing filters capture organic contaminants. Laser spectroscopy, X-ray fluorescence, and ICP-MS instruments measure purity to parts per million levels. If contaminants exceed allowable thresholds, the batch is recycled back into the process. Lithium compounds destined for battery production must be so pure that even tiny impurities can shorten battery lifespan, reduce capacity, or trigger thermal instability. Once purified, lithium carbonate or hydroxide is conveyed to blending and packaging stations inside clean handling rooms. Pneumatic conveyors transfer powder into stainless steel silos where it is mixed to ensure consistency. Automated bagging systems fill lined bags, 25-kilogram sacks or 1-ton super sacks. Each package is sealed, labeled with batch numbers, and placed on pallets. Some lithium is shipped in specialized containers to prevent moisture uptake, as lithium hydroxide is highly hygroscopic and will absorb water from the air. Now the lithium enters the next stage of its industrial journey, cathode and anode material manufacturing. Lithium compounds blend with nickel, manganese, cobalt, iron phosphate, or other metals depending on the battery chemistry. They are mixed in ball mills or high-shear mixers, calcined in furnaces, and turned into fine powders that form the active materials inside EV and energy storage batteries. Though this happens downstream of lithium processing, purity from the refining stage directly determines the quality of these advanced materials. Behind the scenes, lithium processing facilities operate with extreme engineering complexity. Solution tanks use agitators the size of car engines to keep chemical reactions uniform. Heat exchangers stabilize temperatures inside crystallizers. Baghouse filters capture airborne dust from dryers. Pumps, piping, and valves must resist corrosive chemicals like sulfuric acid and carbon dioxide. Control rooms oversee thousands of sensors that track temperatures, flows, pressures, pH levels, and chemical concentrations in real time. Operators use SCADA systems and AI-driven predictive controls to optimize performance and reduce energy consumption. Environmental controls are equally intense. Wastewater must be treated to remove salts and chemical residues. Tailings from hard rock mines are stored in engineered facilities. Brine evaporation ponds are monitored for leakage and water balance. Dust control systems prevent fine lithium particles from escaping the plant. Many facilities recycle water, heat, and process chemicals to reduce their environmental footprint. As demand for lithium grows, the industry moves toward more sustainable extraction, including geothermal brine extraction, direct lithium extraction membranes, and closed-loop water systems. Once lithium reaches cathode factories, its transformation into energy storage becomes tangible. Cathode powders mix with binders, conductive carbon, and solvents, forming a slurry coated onto aluminum foil. These coated sheets are dried, pressed, cut, and stacked into battery cells. Inside each cell, lithium ions will shuttle back and forth between cathode and anode thousands of times over the battery's life. The ability of those ions to move efficiently depends on the purity and consistency achieved at the lithium processing stage. What makes lithium processing so remarkable is the combination of mining, chemistry, thermal engineering, crystallization science, and high-purity manufacturing working together to create the building blocks of the clean energy future. From blasting rock in a mine to filtering brine in remote deserts, from roasting spodumene to crystallizing hydroxide flakes, every step is engineered to produce a material pure enough to store energy safely for years. It's an industrial transformation that takes one of the most reactive metals on Earth and turns it into the backbone of global electrification. And that is exactly how lithium is mined: concentrated, leached, purified, crystallized, dried, milled, and shipped into the battery supply chain. A sophisticated fusion of geology, chemistry, materials science, and industrial engineering powering the world's transition to renewable energy. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines and systems behind everyday products.